All right, hi everyone. My name is Ashna. I'm the Apex Community Manager, and I wanted to introduce you guys to our speakers for tonight. So first up, we have Kenn Knowles, a software engineer at Google and an Apache Beam PMC member, and he's going to talk a little bit about Beam programming and their model and their vision for the future. And then we're going to have Siwon, who's a Apache Apex committer and a data torrent engineer, talk about Apex and its API. So I'm going to hand it over to Kenn, who's going to get us started.
Thank you. I'm going to see if I can. Well, maybe I hold it just as a precaution here. Okay, hello. My name's Kenn. As she said, I'm a software engineer at Google and committer to Apache Beam. And Apache Beam is a programming model and a Java library, soon to be more languages than that, for batch and streaming big data processing. Runs on many backends, and we're kind of hoping Apache might soon be one of them. So I'm going to start by talking about big data in general terms. That's my motivation section, just to make sure we're on the same page about the problems that Beam's trying to solve. Then I'm going to go over the Beam programming model, kind of at a high level. Keep it a bit informal. I hope just interrupt, ask questions at any point, because it's going to build on itself as we go. I'll probably hit the 20-minute mark somewhere about halfway through the model, and I'm going to stop there for like a very brief break for questions to make sure we're there. And then I'll finish the more advanced parts of the model, and I'm going to talk about how the project is going and what our vision for the future is. And I want a lot of time for Q&A, because it's kind of coming out of nowhere for a lot of people, and I want to make sure that we all get to ask everything that we're interested in. Okay, so I'm going to start with the usual motivation and vision here. Apache Beam is model and library for big data processing, and I'm going to use this quintessential example of big data. I'm going to use usage analytics. For example, records of events that are coming from a mobile game that you've distributed that's being played worldwide. So for most of the talk, I'm going to talk about streaming computations over these events as you receive them, but all the concepts apply to like bounded finite data sets, like sets of logs. So here is your incoming massive flow of events from users playing your mobile game all over the world. It's an unbounded data set in the terminology of Beam. You don't expect it to have any end, or at least not for the life of your mobile game, which you hope is essentially forever. And another thing we say about it is that it's widely distributed. The records of events occurring may be delivered long after the events which the data describes, and out of order. So let's look closely at 3 events that happened around 8 a.m. Here's one that we received almost just pretty much immediately after it occurred at 8 a.m. You can see on the horizontal axis there, it's right above the 8 o'clock marker. Here's another one. It came in at 8:30. This is common enough. Maybe they were in a bit of a dead zone for their cell network. And finally, over there on the far side of the screen from me, there's an event that came into the afternoon. Completely normal if the user was playing in airplane mode, or they were, say, camping in the wilderness, but they just couldn't put down your game. So delays of a second, a minute, an hour, many hours, these are just a fact of life now. So you've got this distributed network of sources of late and out of order data, and you want to actually compute some useful aggregation, like a user score. So what are you going to do? You're going to find a way to organize this stream of data into finite windows where the answer is well-defined. For example, you might decide you want to compute results in fixed windows of 1 hour. Perhaps it seems specific enough. You've got finite windows now. You've got windows of 1 hour of data. So you've reduced the problem of unbounded data to that of bounded data, which we have a pretty good idea how to do. But in fact, you have to get much more specific. How do you know when you have all the data for an hour, right? I'm throwing up these 3 events to indicate that you really can't know when you have all the data for an hour. So how do you know when you have enough data to produce an actionable result? It really depends on the application and how much compute power you're willing to throw at it, which you may want to reduce the volume of output to save money, for example. So to see how applications vary, I want to focus on 3 dimensions, which are kind of a core point to the design of the Beam programming model: completeness, latency, and cost. So completeness means the answer you compute takes into account all the data. It means that you have all the data for the hour before you produce a result for that hour. Latency is how long you want to wait until you learn something from new data. Like at one extreme, you wait until you have it all, and that's high completeness, but very high latency. You might be waiting for a long time. At the other extreme, you might want new information to be output whenever any new input arrives. This probably means the answer is very tentative, it's going to be overwritten many times, it's not very accurate, and it could be costly, and that's the third dimension here, since you're performing lots of throwaway calculations. So here on the vertical axis, I've rated importance. Just not important, important, it's all very fuzzy, just to give kind of a ballpark. And on the horizontal axis, I've laid out each of these 3 dimensions. So let's look at specific use cases and how they fall on these axes. Suppose you're writing a data processing pipeline that's going to do monthly billing. Completeness is critical, right? It's sort of the definition of a monthly bill, that you wait until you have all the month's data. So the blue bar for completeness goes all the way up. Latency is not important. That means, so the red bar is super small. Note that the bar being low doesn't mean that we need low latency. It means we don't care that much about low latency. So we're perfectly happy with the latency of waiting till the end of the month. Finally, the green bar on the far right is also very small because we can't really cut corners to achieve low cost when we're computing a monthly bill. Say though, we wanted to give the users a running estimate of their bill so they could avoid surprises at the end of the month. Completeness here is a little bit less important. We're willing to give just a best effort of all the data up to the current time. So I've shrunk the blue bar a bit, but now it's a basic requirement that we get latency down to less than a month at least, so users get feedback in a timely manner. So the red bar in the middle is much larger, indicating we require low latency. However, we shouldn't spend a ton to make this happen because it's not authoritative and it's going to change very soon. So the green bar on the right is a bit larger. This indicates that low cost is somewhat important. The 2 use cases are actually computing the same basic result, right? But because of their goals, they imply a different balance of these 3 dimensions. We really want a way to separate concerns so we can reuse the same processing in both cases. I'm going to move now just to a different domain. We could be attempting to identify users that are spamming or abusing our system. Here, we're likely using heuristic anyway. So our computation probably introduces lots of error all on its own. So there may not be much additional accuracy gained by requiring more complete data. We'll probably converge on a model of an abusive user long before we have all the data for a window that we choose. So the blue bar on the left for completeness is reduced even further. But low latency now is extremely important because we can quickly block problematic users, we're going to save a bunch of money. And on that same note, low cost is not important because if we do successfully block an abusive user of our system, perhaps we've saved a bunch of money, so it's worth investing in that. The Beam model addresses all of these above situations, and I want to just kind of step through how it does so. I'm going to start at the top, which is just the basics of what Beam recognizes as a data processing system. The highest level of the Beam model is going to be familiar to Apex users or users Spark, Flink, Google Cloud Dataflow, or anyone familiar with any of the literature in this area. In Beam, you structure your computation as a graph of transformations, which we call a pipeline. And I'm throwing out this vocabulary, so if you are thinking in Apex every day, just for the purpose of this talk, start thinking in these terms. In Beam, the boxes here are kind of the massively parallel computations, and we call them p-transforms for parallel transform. And the arrows represent the actual data flowing between the transformations, and we call them p-collections. So a p-collection in Beam can be bounded or unbounded. If it's bounded, that means it's finite, and we know that. If it's unbounded, that means it might be infinite. It might still happen to be finite, but we just don't know. So because we recognize convergence in programming models, I apologize. I just added Apex today because I was so excited, and I forgot to include it in the animations that are about to happen. But we recognize a convergence in programming models between major data processing systems. We began incubating as an Apache project. The vision of Beam is to allow you to write a pipeline in your language of choice. Here, I've thrown up boxes of code that represent actual Java and Python Beam code. And then you take your pipeline, and this box in the middle, sum per key, is this language and runner independent semantic description of your pipeline, and then you run it on your runner of choice. Right now, we've got Google Cloud Dataflow, Apache Flink, Apache Spark are in our repository, incubating alongside the initial donation, and Apache Apex and Apache Gear Pump, which is incubating, is those two are in pull requests. They're proof of concepts thrown together already. So we're not 100% here. This is what we are incubating to achieve. This is what Beam is about. So just to make it super concrete, let's walk through kind of an example of Beam Java code. This is the established hello world of the big data world, even though Shakespeare didn't actually write enough to make big data. But so here, this pipeline, first, it uses a text.io.read transform to read all the works of Shakespeare, which we've got stored on Google Cloud Storage in our samples directory. Uses the flat map elements to split the lines on non-alphabetic characters. That could result in some empty strings, so we filter those out. And then we count per element to get a count of each of the words. And map elements transforms formats each word before it's written to a sharded text file using this text.io.write transform. The thing that you should note, right, I haven't said anything about how I'm going to run this pipeline. This just constructs it. And via only command line arguments or programmatic configuration, you can replace what backend it's running on. So when you sit down to write a program like this, we always like to talk about these 4 questions. So first, you determine what it is you want to compute at a very high level. So if you're adding up scores for users of your mobile game, then you want to compute a sum. If you're working on abuse detection pipeline, then you're going to be computing some kind of model of an abusive user or spammer. Then you think about where your data is distributed in event time, and that's time as the user experienced it. How you're interested in viewing it, such as fixed windows of an hour or contiguous user sessions. That's this where question. Then you think about when you want to get output based on this partitioning of your data. Do you want to wait until you're pretty sure you have it all? Do you want early results before you think you have it all? Do you want late results if something shows up a day later? And finally, if you do want to produce early outputs and then also late outputs and just repeatedly refine your result, how do those repeated outputs relate to each other? How do you use them to refine kind of the information you're getting out of your pipeline? So we're going to go through these all in great detail. First, what are you computing? This is the basic reading, transforming, aggregation, and writing of your data. I'm going to illustrate by focusing on a single aggregation. Here is our mental model of users streaming data our way. And before we think about how we're going to manage this data, we can just naively know we're going to do some per user sum. So I guess what that looks like in Beam code and in this sort of illustration style I've adopted is right here, right? On the right, the small squares represent our incoming data with the color representing what user they came from, and the sum per key groups them up by user and aggregates them into those nice little stacks of squares which represent a user's total score. Of course, this code on the left, which I've written, it's sort of actually pseudocode, right? It's not enough to necessarily actually do anything with an incoming stream of data if it's unbounded. Because we can't actually compute the sum over an infinite collection. It probably doesn't even converge, right? So especially not if we're adding up scores. So we need to choose finite windows of the collection if the summation is going to have any meaning. And that brings us to windowing, which is windowing of our input into these well-defined bounded subsets is the subject of the where question. I guess it's about defining at a high level what these nicely organized boxes are from the stream above. If we stick with the mobile game theme, let's choose hourly sum so we can show hour by hour view of user scores. And in that case, each of these boxes represents all the data for an hour, including all users. Recall, however, that the data is delayed and out of order. I'll probably show that animation a few more times because this is extremely important to the Beam model. In order to talk about grouping the data into windows of 1 hour, we have to talk about time. Like how do we deal with the fact that the time that the events actually occurred doesn't really correspond to the time at which we're processing them. So this is a little bit of a tangent that is one of the most important concepts in Beam. Here, I've drawn a completely incorrect notion of time. Each purple square represents some item of data describing an event that occurred. I drew a yellow line for event time. That's the time that the event occurred. And I drew a blue line for processing time, which is the wall clock time when we do something with it. If networks were perfect and processing were instantaneous, everyone was online all the time, this would be fine. But we don't live in this beautiful world. So here, I've separated those two lines. On the bottom, I have this yellow line for event time, and then vertically, I have a line for processing time. This dashed black line is the line we might call real time, where processing time and event time are exactly the same. This is the line along which our beautiful world of perfect networks and instant computation live. If I draw some data on it, I'm drawing these just to emphasize this can't really happen. None of our data can really quite fall on this line. All of our data lives somewhere above the line in its natural state. From this perspective, the height of a datum from the diagonal line is the processing delay for that element. This is the duration between when the element happened and when we did something with it. Here is what a realistic distribution of data might look like. All of our data, it's above the real-time line, and of course, nothing is in the space below and to the right, because that would mean we processed it before it occurred. Many events are going to arrive very close to the real-time line with kind of a predictable distribution to their delay, but there's going to be outliers that are severely delayed, and I've highlighted this outlier at the top of the diagram. So let's talk about organizing these events into fixed windows of 1 hour. A naive way to get hourly results would be to spin up our pipeline, start listening to incoming data, and produce output at the end of each hour. Unfortunately, these results are not usually what you want. Each horizontal band here is 1 hour of processing time. Each hour of event time is marked by these horizontal black lines. You can see that the first hour of processing time, that's here-ish, it actually misses some elements from the first hour of event time. And if you look at the second hour of processing time up here, we've got elements from both hours of event time. There's no hour of processing time that corresponds to these hours of event time. So if you want to know, I mean, the problem is it's not based on the data, right? If you want to know what a user experienced over the course of an hour, processing time windows are unlikely to tell you. Of course, processing time is super important to us because it's how we experience it, waiting for output to be produced. But you don't have to use processing time windows in order to ensure that you get output every hour. That's a separate capability. That's one of the later questions, and we're going to get to that. That's triggers. So an actual hour is experienced by your user. I'm going to just rotate these bars so they correspond to the horizontal markers that I had before. These vertical bands are hours experienced by your user. It's just kind of sensible, right? No matter how long it takes us to find out about an event, the time that it occurred is the same. Event time windows are based on the data. Geometrically, it's really easy to see that any amount of processing delay can never cross a window boundary. So when we talk about windowing in Beam, we're always referring to event time windowing. When you write a Beam pipeline, each element flowing through your pipeline has a timestamp attached, and the timestamp dictates its windowing. Of course, if you really want processing time windows, you can achieve them really easily with event time windows. Event time windowing just means windowing according to the timestamps on your data, and you can adjust those timestamps without breaking anything within some tolerances. To achieve windowing according to processing time, you just throw away the timestamps your data comes with and replace them with processing time. And geometrically, this is pushing all your data to the right until it hits the dotted real-time line. It actually has a very clear logical meaning, which I like to explain that if the original data was a record representing a user scored 10 points, now this modified record is a piece of data indicating the fact that my system learned that a user scored 10 points. It's a perfectly well-defined record. It's probably just not what you're most interested in. So here's how event time windowing is expressed in the Beam programming model in these sweet one-liners. Otherwise, I wouldn't be able to get them on a slide. And looking at the illustration on the right, you can see that the window into transform takes this chaotic data showering from above, and it puts them into these organized blue boxes. And then the sum per key operates per window and kind of aggregating per user within those windows. So we get one row. I guess, given that we're writing to a big query sync here, we're going to see one row per user per hour of event time. So now, we have everything we need to window this unbounded stream, right? No, because I said we'll see one row per user per hour, but when will we see that row up here? So we still don't really know when we can produce the result. Windowing expresses how we would like to partition our infinite stream of data into fixed windows, but it doesn't say what we should do with that partitioning. So for example, I'll repeat the motivation that how do we know when we have all the data for our window, and what do we do then, right? What do you do when data is super late? And also, we might have wanted to produce some speculative output in the meantime. So that brings us to when you want these results to be produced. This covers two fairly important topics, watermarks and triggers. So I'm going to start with watermarks and really dig into that before we move along to triggers. Recall this illustration of event time windows. The vertical bands of color, these event time windows, they really extend forever upwards. So even though we've expressed our computation in terms of these kind of finite segments of the event time axis, we've not actually isolated a finite set of user data or any finite space on this plane. So how do we get something finite from this, right? In more mundane terms, how do we deal with the fact that we can't wait forever, we can't store an infinite amount of data? Well, a naive approach would be to use just a fixed delay from real time. Just ignore any data that appears above that red line. It truncates the top of every band, so we won't have to wait forever. And it also bounds the number of windows that will be simultaneously processed, so we don't have to store an infinite amount of data. It's not a terrible idea, but unfortunately, it is insensitive to our data. We can do better. What if we could just perturb the cutoff into a curve that wraps around all the data? A curve like this is what we call a watermark. We don't usually think of it as a curve. The way we usually think about a watermark is that as processing time proceeds upwards, like so, at each moment, it provides a point in event time up to which we believe our data is complete. So this watermark here, it's pretty much perfect. It never cuts off any data, and yet it progresses very rapidly to the right whenever it's not waiting for data. To explain that again, right here, almost no processing time advances while the watermark advances all the way through the first window. So that's a great property, right? You get a lot of progress. In general, of course, with out-of-order data, watermarks can't necessarily be perfect like this. They can be perfect for some sources of data, like bounded sorted logs, but not in general. So for example, if you're listening to Google PubSub, we use some heuristics to create this watermark. They're actually very, very good. So let's see how a heuristic watermark might actually progress for this set of data. OK, I've faded all the elements to indicate processing has not yet begun. No data has arrived, and we're about to follow things as processing time moves from the bottom up to the top. So here, processing time has begun. I've drawn this horizontal line here, indicates the current processing time. Some elements have arrived. Those are darker purple. And they've arrived in multiple windows. And of course, they're attributed to the window that they actually occurred in. So one element's arrived in the first window, two are in the second window. The watermark has not advanced very far, even though a decent amount of processing time has happened. And it's waiting because it predicts that we are likely to see more data in the first window. Of course, remember, everything up here, the system doesn't know about. It's all prediction. Now, processing time advances a little bit, and the watermark suddenly leaps to the right and completes the first window. So the watermark correctly estimates the first window is complete here. And in fact, even though I said it leaps to the right, it was a little bit slow. It concluded the first window was complete at this point, when in fact, it was complete right there. It would have been safe to declare the first window complete a little earlier. I'm using a laser pointer as though it's just a pointer. But fast forward just a little bit more, right? I'll try using it. You're not going to be able to see it. I like going up to the board. So processing time advances a little bit more, and the watermark has advanced past the end of the second window. In this case, it was a little bit too fast, right? There's some data that's going to arrive in the second window, but it hasn't arrived yet, and the system doesn't know about it. So when data arrives after the watermark like this, we just say it's late. The watermark gives us a notion, thus, like what I'm trying to demonstrate, the watermark gives you this notion of when a window is complete. So it's a measure of completeness, and we can use this to guide when we produce output. So that's not the end of the story, but this is the point at which I'm just going to say the watermark gives us completeness, right? So we can know now, approximately, according to the watermark, when we are ready to produce our monthly bill, when we think we've got all the data for the month. But it doesn't address the low latency use cases. It doesn't address giving a running total. We can't just wait for the watermark to say we've got all the data and then emit output. And it definitely doesn't address the abuse detection story where we need to have some sense of when we've converged, or maybe we just want to continually refine our model. So I'm going to go on to talk about the features that address these second two cases, but I do want to pause for a second because I've been talking for a long time and see if there are any questions thus far. Yeah?
How do you estimate what kind of block function or whatever that your watermark is following? How do you know that you're supposed to sort of stabilize at this particular point? Because you still don't know what is going to come, so that part is not very clear.
Yeah. Just a second. Should I repeat the question to the mic? Okay, so I'm just going to repeat the question is how do we know, essentially how do we know where the watermark should be? Is that sufficient? Or is there?
It's sort of a converging function, right? Something like a log function that sort of moves like this. Well, and somewhere you're saying, okay, this sample is good enough for me to start converging it in the after response.
It's like that. I guess I'm going to move back to here. It's more of just a better diagonal. So the watermark, like if you have a real-time system, right, your watermark is very close to real-time. Then maybe sometimes it's a couple milliseconds behind, and sometimes it's 5 seconds behind, and then it catches up. So it's more just sort of an oscillation around the diagonal in that case. Like if your watermark is continually getting behind real time in that case, then you have a backlog and you have a performance problem. So I guess the watermark, we treat the watermark essentially as a clock, right? It's just a clock that doesn't move continuously. Does that answer? Yeah, so convergence isn't how I think of it. Yeah. Okay. Yeah, in the back.
Hey, so the question is about the heuristic watermark itself. So is there any algorithms which is recommended, or have you seen which makes sense to use in the real-time app?
So yes, it depends on your data source. So the heuristic watermarks are at the sources of your pipeline, and then they're perfectly propagated as just taking a min through all of your successive transforms. So this link, if you find these slides online, you can click on it. Slava Cherniak gave a talk on this at Strata, and the short answer is that this is he describes the special case of PubSub at Google, which is you have one subscription that's actually accepting data and processing it, and you can also find this in the Beam code base. But you have one subscription that takes a little while with each element and it's processing it, and then you have another one that's racing ahead and just kind of learning what's in the queue. And by correlating publish times and the event timestamps, they kind of keep a heuristic of what event timestamps are expected to show up in the future.
Okay, so is it safe to assume that the watermarks are actually generated by the first stage in the pipeline?
Yes.
Or is it coming actually from the source itself?
It is the first stage in the pipeline. So I guess if you have a data source that's it's a connector, right, to some external system, and that external system may or may not have a notion of progress or time or watermark. And so when you write a connector like Kafka.io or PubSub.io in Beam, that's when you have to think about how do I know, how can I measure progress against this data source?
Okay, thank you.
Yeah.
And till now you've been talking about mostly tumbling window kind of approaches, right? Is there also a sliding window, moving window kind of stuff?
It's harder to draw on a slide. So the watermark itself is independent of the windows. So if you can imagine, I could have many, many overlapping rectangles here that I couldn't illustrate super easily, but we tend to draw them stacked vertically on top of each other if we need to draw them. And the watermark still estimates, essentially, it's independent of the windows. It just estimates what time it is, and you compare that to the end of the window and decide whether or not you think you have all the data for the window. So does that answer your question? Okay. You know what? Okay. I'm going to advance to here, and now come back to the fact that we have a measure of completeness. That is what the watermark gives us in terms of these graphs that I've tried to recall here. And now I want to talk about how that measure of completeness interacts with you really being able to customize when you receive output. So the when in processing time starts with watermarks and it ends with triggers. Triggers are user-written expressions that govern when output is permitted to be created. So the trigger that would correspond to outputting when the watermark says you've got all the data is this after watermark trigger in Python, which in Java is spelled after watermark.past of window. And this says just once we think we have all the data, output it. I've given up on illustrating it because at this point we really need a two-dimensional diagram to see what's going to happen. So let's try walking through exactly how this trigger interacts with the watermark on this example here. So it's the same setup as before. Everything's faded out. No elements have arrived. Processing's not yet begun. Now I'm advancing processing time, and the watermark estimates the first window is complete, right? So we output an aggregation. Let's say I'm not going to specify what the aggregation is, but I might accidentally call it a sum. So we output this aggregation for that window, and it just includes this one element that's arrived in the first window. Note there's an element arrived in the second window, and it's just sitting there buffered. Because we can see the future, we know that some more data is going to arrive in the first window, but the watermark doesn't know that, of course. Now I'm fast forwarding some more. Processing time moves all the way up to here, and the watermark has advanced in its little meandering path through the second window. And so an aggregation is emitted for all of the elements that arrived in the second window. The additional element showed up in the first window, but it was too late to be included. There's a configurable allowed lateness after the watermark, but I'm just leaving it at 0 so that we can demonstrate the fact that eventually data will become so late that it's dropped, and that's something that you can control. So that's the simplest watermark in some sense. No allowed lateness, you don't have to deal with late data, you don't have early data. And if we look at the entirety of this execution, and let's look at it in terms of these dimensions, we can see it's high completeness because we wait until all of our data has arrived, or so we think. It's potentially high latency because we're waiting so long. And it's very low cost because you could have a cajillion elements show up in one of these windows and you're still only going to have one output. So the volume is about as small as it can get. So let's turn now to triggers that actually trade off completeness for latency and cost. The trigger up here, repeatedly, forever after paying element count at least 2, is how in Beam we say that we would like new output whenever at least 2 elements have arrived. In practice, you'd use a much higher number, so this is just for the slides. It's totally independent of the watermark now. I'm just counting elements. So it just ensures when we've got some data, we're going to produce some output. So here, processing time advances a little bit. 1 element arrives in the first window, 2 elements arrived in the second window. So output is produced in the second window. The watermark's barely advanced at all, of course, so I'm emphasizing that it's not related to the watermark anymore. And I'd also, I guess I just want to emphasize also that it's driven by input volume. So let's move processing time a bit further. The watermark is still kind of barely advanced. We got 2 elements in the first window now, so output is produced. Note, the outputs to the windows are produced out of order. Even though we're windowing, it doesn't sort your data and try to do anything that way. Progressing just a little bit more, 2 more elements, and arrive. Another aggregation is emitted for the second window. Now, think for a second just about the downstream transforms. They're going to receive multiple aggregates for each window. We actually have a few choices, right? It's going to receive an aggregate here for the first 2 elements, and then another aggregate that somehow takes into account all 4 elements. We have a few choices about how to communicate these new aggregations, and I'm just calling that out as I'm going to talk about that next, that's something that you should be curious about. Like, what do I do if I emit a sum and then I emit another sum? How is that managed? This example isn't quite done. Even though all the data has been received and emitted, I'm going to advance processing time a little bit more so that the watermark advances past the end of the second window. And why do we care? Well, in Beam, after the watermark declares a window complete, there's some fixed allowed lateness. And after that, anything that shows up can be dropped. So the window is considered expired. And that means the runner is free to actually discard any new data and discard anything it ever knew about this window. So that's kind of important, right, to make sure that your runner doesn't have to maintain an unlimited amount of state. So even when the trigger ignores the watermark, it has a role to play in the implementation of a Beam backend. And again, stepping back, looking at the entirety of this execution and how the output policy relates to these 3 dimensions. It's low completeness. It doesn't care about completeness at all, so you would never choose this if that were important for you. It's low latency, right? If you're getting a flood of input, you're going to get constant output, but the cost is driven by the input, so it could be quite high. It doesn't reduce the cardinality input particularly. The prior 2 examples were sort of basic building blocks, but Beam includes combinators, so you can build more complex triggers that are tailored to your use case. So I want to walk through this one. I've started with the first trigger we looked at, the after watermark past end of window, which says send the bill at the end of the month. And the base trigger then, to that I add early firings after processing time past first element in pane plus duration standard minutes 1, which is the Beam way of saying after you receive some input, you kind of set it after a minute, you should emit some output. So that you are sort of setting kind of a heuristic lower bound. Heuristic's not the right word. It's not strict that I output before 1 minute, but you're going to get output around a minute afterwards. And in effect, I guess you'd say it's sort of throttled to 1 minute. And then this will give us our near real-time estimates of kind of the running total that a user is going to want to look at when they go online and check out their account. And then we've also specified with late firings after pane element count at least 1. So this says that whenever an element arrives late after we already sent the bill, immediately send a revision to the bill, right? So let's see how this evolves. We're going to focus on just one window. Initially, 2 input elements arrive, and they're buffered. The watermarks hardly move. None of our trigger logic says we should output, so we're just waiting. Pausing for a second. This sort of early firing has some good properties. Let's see here. There we go. You're never sitting on knowledge. Oh, sorry. OK. Processing time advances 1 minute. I buffered them. And then 1 minute of process time advances, and I've emitted some output that takes into account. It's an aggregate of these 2 elements. This early firing has the good properties that it's low completeness, right? We're not waiting until the end of the window. And it's low latency. It's bounded by this processing time timeout. But it can also be low cost because it's driven by processing time, right? You can have a ton of elements arrive within that timeout, and they're all going to result in one aggregation. Moving along, after the watermark progresses all the way past the end of this first window, we have another aggregation. These 3 elements are the ones that arrived in the time when the watermark, before the watermark passes the end of the window. So now we're going to emit this aggregation of those 3 elements, and it's going to be labeled on time. And that says, this is what I think is the authoritative aggregation for that window. Downstream processing can do things like send a bill, because you know that this is what you consider the on-time output. Of course, we know, since we are looking at what's about to happen, that some more data is about to arrive. So moving on, when the late output shows up, because we've got this trigger that says after every element, immediately emit output as soon as you can, we emit a new aggregation that takes into account all 4 elements. It's like a revision to your monthly bill emitted as soon as possible. This trigger is a prime example of how you can use Beam's language of triggers to assemble a trigger that's right for your application. I've shown these few examples. Beam has a rich catalog of triggers. It's the nature of slides to get out of date. So you should refer to the Beam documentation to discover all the triggers. But I'm just going to review what we've seen and go over a couple others. So we saw that triggering after the end of the window can give you fairly complete data. Then we used after count trigger to produce output whenever enough input had arrived, and we looped it with repeat. And then we demonstrated how you might be able to get lower cost, low latency results by triggering after a processing time delay. And finally, I showed how you could augment the after end of window trigger with early firings and late firings to have kind of a trigger that changes over time. In addition to these, there's a simple after any trigger it's a combinator that produces output whenever any subtrigger is ready, and the after all trigger, which is a combinator that produces output once all of its triggers are ready, all of its subtriggers are ready. You saw the repeat trigger, which just repeats the trigger forever, and you can also simply sequence triggers. So that's triggers, and now I want to dig into kind of zooming in on when you emit output more than once. That's how do these refinements relate. Each output is a refinement of the prior, and that we call accumulation mode in Beam. Here's an example of being quite explicit about the accumulation mode. I'm going to go over it pretty quick because it's a fine detail. You're going to, you'll learn more by studying it later, and I really want to talk about the progress in the project and not simply talk about the Beam model. So let's look at this. We apply a window into, we specify some windowing here, and then we specify triggering, and we say discarding fired panes. And so over on the left is where I've illustrated that. These elements are coming in this order. So first, I get a 1 and a 4. Actually, sorry, let's say they come in here. We get a 3 and a 7, and they come in one batch of data that I'm going to process, and then I sum it, and I output this 10. Now, I don't remember that 10. I just forget about it. I've summed the stuff that came in. I've emitted some output because whatever trigger I specified said it was OK. Then another batch comes in, and it has a 1 and a 4 in it. So I sum that, and I emit a 5. So you can see I'm sort of, what the total sum would be here is 15. And what I'm doing is I'm emitting kind of incremental, they're incremental sums. And so you'll need downstream, if you wanted the total sum, you would sum these up. The alternative to this that exists in the Beam model is accumulating fired panes. And this means that when you emit output, you remember what that output was, what you had accumulated. So if the 3 and 7 come in, and I'm going to add them up and get 10, and I emit this 10 down below, but instead of throwing it away, I keep it around, and then when this 1 and 4 come in, the total sum is 15, and I emit a 15, right? And now if you look at this pattern of output, I have a 10, then a 15, and what's downstream should treat the most recent element coming out here is a complete replacement for what came before. So that is just kind of the briefest overview of how you need to think about how multiply triggering transforms, how the refinements of your output relate. So if you do remember one thing about the Beam model, remember these questions. What are you computing? Where in event time is your data, and how do you want to look at it? When do you want results to actually be produced? And if you're producing results more than once per window, how do those refinements relate? This is the high level. So now I'm going to take whatever time I have, which is not a ton, but I'll go slightly over into the Q&A time just to talk about the project. We're an Apache project, and we got an Apache bug tracker and mailing lists. I'm going to talk about all that, the GitHub pull requests, the web page. So the Beam vision started when we had cloud Dataflow at Google, and we, from the very beginning, envisioned multiple backends running these programs. We never wanted lock-in, right? So we open sourced the Dataflow SDK, and in fact, people did write other backends for it. We had a Flink runner was written, and a Spark runner was written. And so those existed, but it wasn't an ideal workflow because we would work internally and throw stuff over the wall, and it would break everybody who was working outside, and it wasn't a community at all. So what we started to think about were 3 groups of users. We have end users. We want to keep them happy. They're the ones who want to write pipelines. They want to write pipelines in a language that's familiar, and that's why we have a Java SDK and a Python SDK. And there are SDK writers, who are the people maintaining this stuff, and they want to make Beam concepts available in their language of choice. So maybe other languages. Maybe somebody wants to write a Ruby SDK or an R. And then the runner writers. They have a distributed processing environment like Apex. That's you guys in the back of the room. And you want to be able to run Beam pipelines, and you want to have a stable API to work with. So the vision that we have many backends executing, many pipelines in many languages is where we came from in this. We had the Google Cloud Platform. These are our GitHub repos. We had the Google Cloud Platform Java SDK, Cloudera, Spark Dataflow, Data Artisans, Flink Dataflow. It all got donated into the Apache Incubator Beam repo, and that's where it lives now. And so now, in this repo, what we have evolving is we have an in-process runner, we have the original, the Dataflow runner, Flink runner, Spark runner, and in the pull requests, we actually have an Apex runner and a gear pump runner. So we're reviewing these, and we're going to bring them in, as soon as we can. And I guess the benefit of all of this stuff getting into the same repo is that they all share cross-runner examples, cross-runner integration tests, and I/O connectors, right? We're trying to grow the set of I/O connectors, so you can connect to HDFS, Kafka, BigQuery, GCP products like Bigtable, PubSub, and Google Cloud Storage. And there are a couple in pull requests, and lots have been proposed. And this is sort of what's happening in terms of like how the code is organized and what lives together and why it lives together. And since we started, it's been super awesome. It's been an amazing experience. We got committers right off the bat from Google, Data Artisans, Cloudera, Talend, and PayPal. And the cadence was about 40 commits a week, and these are including code review on every commit. It's been, we're keeping, it's the Google practice, and we're keeping that in order to keep the quality bar super high. And we've also gotten contributors just coming out from, I'm just going by the GitHub badges, not claiming specific affiliations other than that. We got Spotify, Intel, Twitter, Capital One, and I'm saying Datatorrent because we got pull requests that came in. And they've contributed new runners, improvements to existing runners, new I/O connectors, and including stuff that we're always asking for, like documentation fixes and bug diagnoses. It's been just wonderful contributions all around. So if your name here, I would love it if you in this room were the next contributor that I could put on this slide. And I'm really excited about the Apex Runner proof of concept. So now in terms of where we are in our actual project goals, like setting aside all of my excitement about it, we had Dataflow Java 1x. It's moving along. This is a Google product. And we donated the code right here. And these little red explosions are breaking changes. We have lots of changes we wanted to make to the API, and now's the time to make Beam as polished as it can be. And we're kind of right in the middle of doing all of that. And once we hit a stable point, we're hoping late 2016 here, we're going to release Apache Beam Java 2x, and that's going to be the first stable release of Beam with backwards compatibility kind of assurances. In terms, you can follow, we'll obviously be giving periodic updates at meetups like this about how that's going, but also you can follow online if you want to look at what the capabilities of all the runners are. We keep matrices because we have all of these features in the model that I've just talked about, and they're supported to different degrees by different runners, and that's expected and fine, and so you should go to the web page and check out the capability matrices we maintain there so you can see what backends are supporting what features. So I guess I've talked about why Apache Beam quite a bit, but I just want to hit the bullet points, which is that we want one model to handle batch and streaming use cases. That's where data processing is going. And we want it to be portable, so pipelines can be executed on multiple execution environments. We don't want anybody to be locked into any particular backend. And we want it to be extensible. We want, if somebody wants to make a Beam SDK in, I don't know, let's say Groovy, we want them to be able to do that. So there are also these superb quotes that I just want to throw up on the slide, right? Tyler Akidao at Google, he, on this public blog post, says, we want this healthy ecosystem. We want runners that compete by making users happy, not by lock-in. And from Data Artisans, we have Kostas Somas saying, we firmly believe that the Beam model is correct programming model streaming and batch for data processing, right? So we have just wild agreement among some big names in data processing that this project is a good idea. And so we're trying to create this community. We're bootstrapping right now. We would love to invite everybody in. We're becoming community driven, and it's happening, and we love contributions, so do join us. And here, I hope this is enough that you're excited and you want to go learn more, so go to the Beam webpage for sure. Read the Why Apache Beam blog posts from Google and from Data Artisans. And for more detail on the programming model, Streaming 101 and 102 are O'Reilly articles by Tyler Ekadow, which are superb, in my opinion. And then he also co-authored the Dataflow model is the title of the paper, which is now the Beam model. And of course, go online and join the community. Join our mailing list and follow Apache Beam on Twitter. That's the end. Any further questions at this point? I looked at the back first, so you're nice.
Hey. So previous slides you mentioned about allowed lateness.
Yep.
So I guess that's with respect to the watermark, right?
Yes.
And is that on the processing time axis or event time axis?
So the way there, so I want to first, if you're super interested in this, there's a technical document on the Apache Beam website in our technical docs folder. There's a document called lateness in Apache Beam, and that goes over it in detail. And the way I think about it is that there's a garbage collection watermark that exists behind the normal watermark. And the way we implement it is just by adding a constant to the watermark. But in fact, a runner, I think, would be reasonable to implement it a different way if they wanted to.
Okay. One more question was, so the watermarks that you said previously would be initiated from the first stage of the pipeline. How frequently should that be done?
So I don't own that corner of the API, and I don't look at it too closely, but I believe it's on a pull-based method. I think that when you write an I/O connector, you write a get current watermark, right? So I don't think this answers your question. Like how often? Like maybe you're actually just caching that and updating it once in a while. I don't know that there is one true answer for how often you should update that. There was a question in the front. Just for,
yeah. So what is the over database SDK for this very high performance backend? So we can do native and Apex versus going to Beam for the same function.
Right. Well, and also so we don't. It would be specific to the runner. So you need to write this bridge, right? You have the SDK, and then you need to translate it or interpret it on Apex, and it would really, that code can be optimized, and that needs to be.
Do we have any numbers on that?
Well, we don't have any numbers for Apex because it's not done yet. But I don't know any numbers off the top of my head for our existing runners.
Yes, one more question regarding watermarks. So you solve the propagation of window information with the windowed value in Beam, right, where you wrap the actual data tuple. Is there a reason why something similar doesn't exist for watermarks? Is there any plan to also specify how the watermarks are propagated through the topology?
So that's a great question. So I believe that Flink has a native idea of watermarks, and I am absolutely not an authority to speaking on this, but I will just say that if you have a data stream that's based on punctuations, you can certainly have watermark updates as a punctuation in the data stream, which I think is roughly what you'd be talking about there.
Yes, this is how we would solve it. I was just curious whether there's a decision or what the motivation might have been to not do it similar to the window information where you actually piggyback it on the data.
I don't really know the history of the decision.
Okay.
Yeah.
Thanks.
Mm-hmm.
Okay, so at the at-scale conference, Google presented a full version of it with the watermark and all that. So how did that one relate to the Apache Beam?
I'm not familiar with that. Sorry. Okay. Well, over time. So thanks for listening.